If I ask you to plot the square root of 9 on a number line, you know exactly where it goes. It drops perfectly onto the 3. But if we change that number slightly to the square root of 9.3, finding that precise location with arithmetic alone becomes surprisingly difficult. You can estimate, but math demands precision. Guesswork won't get you a perfect plot. Instead, we are going to use a specific 5-step geometric method to find the exact location of any decimal square root. Grab a blank sheet of paper, a compass, a ruler, and a protractor. Our objective is twofold. First, we will physically construct the line representing the square root of 9.3, and second, we will mathematically prove that our construction is correct. To solve decimal roots accurately, we have to put down the calculator and rely on physical geometric construction. This notebook lays out the precise steps for our construction. Step 1 is straightforward. Draw a line segment exactly 9.3 units long, from point A to point B. The critical next step is to extend that line from point B by exactly 1 additional unit, ending at a new point, C. The total length of segment AC is now 10.3 units. Next, find the exact midpoint of this entire 10.3 unit line. We'll label this point O. Place your compass needle at O, set the radius to stretch to either A or C, and draw a sweeping semicircle over the line. Now, return to point B, the original 9.3 unit mark. Draw a line straight up, exactly perpendicular to the base, until it intersects the roof of your semicircle. We'll call this intersection point D. The length of that new vertical line segment, BD, is exactly the square root of 9.3. The drawing phase is complete. Now we must verify why this height is mathematically correct. This diagram shows the geometry we just built. To prove the length of BD, we need to focus on the right-angled triangle formed inside the semicircle, triangle OBD. We can determine the length of the hypotenuse, OD, by recognizing it is a radius of the same semicircle we just drew. Since the total diameter is 10.3, the radius, and our hypotenuse, is half of that, 5.15. Think about the base of our triangle, segment OB. The distance from center O to the end C is our radius of 5.15. Subtract the 1-unit extension, BC, and what is left for the base? Exactly 4.15. With a hypotenuse of 5.15 and a base of 4.15, we can set up the Pythagorean theorem to solve for our vertical line, BD squared. At this stage, it is tempting to start multiplying 5.15 by itself, but manually squaring decimals of this size is tedious and leaves too much room for calculation errors. Verifying our geometric construction is now an algebraic problem. We need a smarter, more efficient calculation strategy to solve it. Look at the right side of the calculation steps. We can use the algebraic identity for the difference of squares. A squared minus B squared equals A plus B times A minus B. This bypasses the complex decimal multiplication entirely. By adding 5.15 and 4.15, we get a clean 9.3. By subtracting them, we get exactly 1. Multiply those together, and BD squared equals 9.3. We've mathematically proven that the line segment BD is exactly the square root of 9.3. To finish, we need to translate this vertical value back to a horizontal format. Place your compass needle at point B, extend it to point D, and sweep an arc downward until it intersects your extended horizontal number line. That exact point is the square root of 9.3. This method applies to any decimal square root. Here is your universal checklist. Draw your starting value. Add exactly 1 unit. Draw a semicircle from the midpoint. Raise a perpendicular line from the original mark. Finally, sweep an arc down to the number line. By combining basic geometric construction tools with a simple algebraic shortcut, you can precisely plot and prove any complex decimal or irrational number on a standard number line.